some lights here. So now we're going to calculate this thing called the moment of inertia. So let's calculate. It's often, when we're being cool, we just call it the moment. Moment for point mass. All right, okay. So let's see. So let's imagine that we have like a big barbell here, like this. This is very familiar to me here, like that, right? All these giant things, you lift it and the thing bends, it's so light. And the length of the thing is L, and these are huge masses here, right? And the bar is light, right? The bar doesn't weigh much. If you're not given the mass of something, it either is so light you don't consider it, or it's going to cancel. Hint, hint, pledge problem. If you're not given the mass, just put M. It'll probably go away. So we want to calculate the moment of that thing. So can I just start calculating the moment? No, because I've not given myself an axis of rotation. Let's calculate the moment around here. Let's make this the axis, like into the board. Okay. So in that case, since these are discrete masses, we can treat them as just point particles. Okay, we'll do examples where you don't just treat them as point particles later, but for now, it's just two masses. And you just use a formula. The moment I is the sum over all the masses of the mass times its radius or its position squared. So that looks kind of ugly and weird, but it's just saying add each one up. So the fundamental thing to know is that the moment of a mass is the mass times how far away it is from the axis squared. It goes as distance squared. That's why the unit is kilogram meters squared. So if we wanted to get this moment, we'd say I, the moment, is the first mass, M, big M, times this R squared, L over 2 squared, plus, I'm just getting started. Okay, whatever. Plus this mass. It's big M times its distance, L over 2 squared. All right. So the answer is M times L squared over 4 plus M times L squared over 4, M times L squared over 2, because the 2 1/4 add up. 1/2 mL squared is the moment for those two masses. So I'd say the only thing confusing about that is but one is in the negative direction, one is in the positive direction. So the thing to know is mass is a scalar. It is not in any way a vector. It doesn't depend on direction. Okay? Mathematically, it even works out. You could put a negative in there if you want, but you're going to square it. That's your mathematical hint that the direction probably doesn't matter. If you put a negative sign in, it wouldn't matter. It'd still come out squared. So, but you might say, well, then shouldn't the side it's on affect the angle, the direction it goes? No. There's no vectors here. We're not doing kinematics. We're just calculating the moment. We're just calculating how some number related to how the mass is distributed around this axis. This 1/2 mL squared applies if you rotate it this way or if you rotate it this way. It doesn't really matter. It has nothing to do with gravity or anything like that. Okay, so don't worry about which side is positive, negative for moment. For torque and everything else, of course, it matters. Right? But for moment, it's special. It's just a property. If you want intuition for this, you take one of these. See this? This is a rod with a heavy mass at the bottom. Right? And I'm going to try to rotate it around here, this axis. And to do that, I have to use my hands. I'm really applying a friction force, a torque, around this little part to try to make a big enough torque to lift the whole thing and try to get it all the way up to hold a static torque. And it's like I can almost do it. I can't quite get it up. It don't quite go all the way up. I'm not strong enough. Okay? I have a physique that can only be achieved through a lifetime of not lifting weights. Okay? I should be studied for that. But if I put the mass here, now even easy, right? Look at that. Be impressed. Yes. There you go. Yes. So what I've done is I've changed R from the full length, L squared, not just L squared, down to just some teeny, like 1/10 of L squared. And then it's easy to turn. Okay? Now, if you're smart, how many of you are smart? That bad, huh? Okay, so if you're smart and, you got some really strong people making fun of you and they're like, I bet you can't torque this and rotate it, and you can't, right? All you do is this. You didn't say the axis, right? There you go. I can turn that, right? That's another case where we've got to think about how the mass is distributed around the axis. If you go with this axis, then all this heavy mass is even closer than when I had it up here next to this axis. It's really close right here. So that's why it's easy to turn this way. It's just hard to turn this way. And it's hard to turn this way. Oh, I'm a little better at that. If you want to play during the 5-minute break and get a feel for this, you can play with these. You could even take these to a party if you want. Like one has all the mass here, and one has all the mass here. So it's very disorienting. Yes, so play with those. I don't know. I'd never seen those before. Somebody gave it to me right before class. So I'm not sure what to do with those. Like if you're going to fight with them, I'm not sure which one it's better to have. Maybe y'all can figure that out. Okay, so that is the simplest idea for moment. If you just have point masses, it's just mass times how far it is squared.